The mean value theorem for integrals. Objectives. By the end of this lesson, you should be able to find the average value of a function over a given interval, understand the graphical representation of the mean value theorem for integrals, apply the mean value theorem for integrals, and understand the difference between average value and average rate of change of f of x.
Alright, before we look at the formal statement of the mean value theorem for integrals, I want to do a little review. So, if you were asked to find the average of two numbers, the two numbers being 10 and 20, the expression that you would set up would be 10 plus 20 divided by 2. So I'm taking the average of two numbers, so I know that to be adding the two numbers together and then dividing by the number of numbers I'm adding together. So in general, if we have a finite collection of values, a1, a2, up to some an, to find the average, or the mean, we use the formula a1 plus a2 plus up to an divided by n, the number of terms that we added together. So we're used to finding the average of a finite number of numbers. So what's going to happen if I attempt to find the average of an infinite collection of numbers is the question I'm about to pose.
Alright, so now what if we want to find the average of an infinite collection of numbers, specifically all the values of a continuous function over a particular interval? So let's make this a real-world application. Let's suppose f of t is a function that represents temperature as a function of time. Then f of t is a continuous function, and we might wish to consider something like the average temperature over a period of time. So let's draw this. Just going to go ahead and draw a xy plane, or in this case, a t f of t plane. So on the horizontal axis, I'm going to have t, and let's say my time is in hours. And this function, f of t, represents temperature. So let's say the units on the vertical axis are degrees Fahrenheit. So I'm just going to go ahead and draw any function here. Let's say my temperature function looks like this. So this is f of t. And what the points on this graph represent, so let's just pick some time, let's call it t1. If I go up to the function at time t1, the output is going to be how hot it is at that time. So after 1 hour has passed, it's 60 degrees Fahrenheit. So that's what the points on this graph represent. So now we might wish to consider the average temperature over a period of time. So now we're going to need some other time, t2, so I can consider an interval of time. And we're thinking average, so we're thinking we want to add a bunch of stuff together. Well, what we know how to do is we know how to add the area under a curve. So we can, using our knowledge of integrals, if we were given f of t explicitly, we could find all of this area here. So let's set up that integral, the integral from t1 to t2 of f of t dt. So we could, if given f of t in time 1 and time 2, find this exact area. Now, let's think about the units of that area. The units of the base, we called our units of time in hours, and the units of the height is in degrees Fahrenheit. So when I multiply to find area, and think of the units as base times height, I'm going to have degrees Fahrenheit times hours. So the units of this is going to be some number, then degrees Fahrenheit times hours. And now let's think, I wanted the average temperature. Degrees Fahrenheit times hours is not a temperature, right? It's not even a rate because it's not per hour. It's degrees Fahrenheit times hours. So now what I want to do when I think of average is I want to divide by however many things I added up. Well, technically I added up infinitely many temperatures, but they spanned from a time frame from time 1 to time 2. So what I'm going to divide by is the total time elapsed. So the total time elapsed here is really t2 minus t1. So notice t1 and t2 were the limits of integration, and that is what I'm going to divide by. So if I divide by t2 minus t1, well, t2 and t1 are hours. So now let's think about what's going to happen to my units. I had some number, degrees Fahrenheit times hours. If I subtract two times from each other in hours, I'm going to have a unit of hours in the denominator, meaning my units of hours will cancel so that I end up with some number Fahrenheit. And that number is the average temperature over that time frame. So we're going to generalize this because this represents the average value of a function over a particular interval. Alright, so the average value of a function. The average value of an integrable function f of x on the interval from a to b is given by, so f average equals 1 over b minus a, the integral from a to b of f of x dx. So another way we can think about this is the integral from a to b of f of x dx, so it's all the area under the curve from a to b, and then divided by that total distance between b and a, so b minus a. So now this looks a little bit more like the average concept that we know, where we add up a bunch of stuff. Remember, integrals, we're adding up a bunch of area, and then divided by however much we're adding, so that distance between the two endpoints of my interval. And average value is also called the mean value. So average and mean are synonymous. So graphically, what's happening again, so we just sort of drew a picture of this. So now we have some function f of x, and we have some interval from a to b. So we're finding all of the area from a to b, and then we're just dividing by this total distance between A and B that's happening. So to find this distance, well, B is the bigger number and A is the smaller one, so we subtract A from B. So what goes on the bottom here is B minus A.
So some examples like this one are going to be really straightforward. So consider the function f of x equals x squared on the interval from 0 to 2. Find the average value of f of x on this interval. So what I'm going to do is set up f average, which is 1 over b minus a, so 1 over 2 minus 0, times the integral from 0 to 2 of x squared dx. And now it's a matter of solving this integral. So I have 1/2 the integral from 0 to 2 of x squared dx, or 1/2 times, using the fundamental theorem part 1 here, I get x cubed over 3 from 0 to 2, or 1/2 times, substituting 2 in, I get 2 cubed, which is 8 over 3, minus substituting in 0, I get 0. So I end up with 8 over 6, or simplifying down, I get 4 divided by 3. So 4 over 3 is going to be the average value of the function over the x interval from 0 to 2. So now that we have the definition of what it means to be the average value of a function, we can look at the formal statement of the mean value theorem for integrals. So the mean value theorem for integrals says that if f of x is some continuous function on this closed interval from a to b here, then there exists a value c in the closed interval from a to b such that f of c equals 1 divided by b minus a times the integral from a to b of f of x dx. Or another way to say that is the integral from a to b of f of x equals f of c times b minus a. So that would be just moving this quantity here, this b minus a, multiplying it to the other side. So let's take a second to just stop and think about this. So we have a continuous function on a closed interval. Then there exists a value c in this closed interval from a to b such that the function evaluated at c, is equal to the average value of the function. So this portion over here represents the average value of the function. So it represents f average. So if the function's continuous, there's some value between a and b that's equal to the average value of the function. Or again, another way to look at it, and this is the way we're going to focus on for just a second, is that the integral from a to b of f of x dx, so all of the area trapped between the curve f of x on the interval from a to b, is equivalent to f of c times b minus a. So let's look at what that means on a graph. So let's say here's my curve f of x, and I want to find the area from a to b under the curve f of x. So here's a, here's b. All of this area here is the integral from a to b of f of x. So what the mean value theorem says is that there's some value between a and b such that I can say that the area under the curve of f of x from a to b is the exact same thing as the area defined by this formula here. So this formula here is actually the equation for the area of a rectangle. So the rectangle has base b minus a, and there's some place c where the function value evaluated at c defines the height of this rectangle. So there's going to be some c value between a and b that defines a height of a rectangle that's exactly the same area as the area under the curve from a to b of f of x. So to show what that means on this graph, what I'm saying here is that this rectangle's area, so we'll shade that in a different color, this red shaded region is the same amount of area as the blue shaded region. So the mean value theorem says that there's some place C between A and B such that I can find that function value and make it the height of a rectangle, and that rectangle's area is the same as the area under the curve f of x from a to b. Alright, so just a quick second to look back at the mean value theorem for derivatives. So we don't really say that, but it's implied. So just a quick visit back. So f is a continuous function on the closed interval ab and differentiable on the open interval ab. Then there exists at least one value c in the open interval from a to b, such that f prime of c equals f of b minus f of a over b minus a. So notice that there's a little bit of the same structure happening. So there's at least one value c. So the mean value theorem for integral said there's some value c in the interval. Well, the mean value theorem for derivatives says that there's some place c where the slope of the tangent line is the same as the slope of the secant line. So the mean value theorem for integrals says that there is some place c such that when I define the height at f of c and I draw that rectangle, that rectangle is going to give me the same area as the area under the curve. So just kind of a little comparison of the mean value theorem versus the mean value theorem for integrals. Alright, let's look at another example. So suppose f of x equals x minus 3 squared. Find the average value of the function on the interval from 2 to 5, and then find the value of c in the interval from 2 to 5 such that the average value equals f of c. Then sketch the graph of f and a rectangle whose area is the same as the area of f. Alright, loaded question. So first, find the average value of the function on the interval from 2 to 5. So here's my function, f of x equals x minus 3 squared. So I'm going to write it as x minus 3 times x minus 3 to arrive at x squared minus 6x plus 9. So if I want the average value, f average is going to be 1 over 5 minus 2, the integral from 2 to 5 of x squared minus 6x plus 9 dx. So I'm going to get 1 over 3, the integral from 2 to 5 of x squared minus 6x plus 9. Now with a lot of algebra, I'm going to get 1/3, and evaluating this definite integral here is going to give me 3. So 1/3 times 3 worked out nicely. I get 1. So the average value of the function on the interval from 2 to 5 is going to give me 1. So now we want to find the value c in the interval from 2 to 5 such that the average function value on 2 to 5 is the same as f of c. So we know that the mean value theorem for integrals says that there's some value c such that f of c equals the f average. So f of c has to equal 1. So in other words, what value do I plug into the function to get out a value of 1? So f of c is going to end up being c minus 3 squared equals 1. So here, if I take the square root of both sides, I'm going to have c minus 3 equals plus or minus the square root of 1. So c equals 3 plus or minus 1. So I'm going to end up getting two values out, c equals 4 and c equals 2. But the interval I'm concerned with is from 2 to 5. So 2 actually happens to be one of the endpoints, and then 4 happens to fall within the interval. So we did find the value, or actually values of c in the interval that satisfy this equality. So there's 2 and 4. So the very last thing we're going to do is sketch the graph of f and a rectangle whose area is the same as the area under the graph of f. So sketching this, x minus 3 squared, well, we're going to have to go back to pre-cal for a quick second. The parent function here of x minus 3 squared is x squared. And then when I subtract 3 from the x coordinate, this is going to be a shift to the right 3 units. So the x squared function moved right 3 units here. So it would normally be over here, x squared, but x squared minus 3 is going to be shifted to the right. So it's going to look something like this. And it should have touched the x-axis there. So what we found was that between 2 and 5, so here's 2 and then way over here at 5, so we want to find a rectangle whose area is the same as that of the area under the curve between 2 and 5. So let's shade in the area under the curve for a second. So I guess I should extend this a little bit more. Whoops. So go all the way up to the function, and then all of this area here. I want to draw the rectangle that's going to give me the exact same area, and I know that the height of that rectangle is going to occur at the values of c that we just found on the function. So let's use a different color. So now here, I know that at 2 and at 4, I can go up to the function at either of those values and draw a rectangle with base between 2 and 5. So let's say at 2, if I go up to the function, that'll be the height of a rectangle that I'm going to draw that has a base between 2 and 5. And the area of this rectangle is the exact same area as the area under the curve. Now, I could have also chose to go to f of 4, because if you'll notice 4 here goes to the exact same height. So either of those heights will work. So there are actually two values, and the mean value theorem says that there is at least one point. So we found 2, and that's absolutely fine, and both of them yield the same height, so that the rectangle we create will be the same, and that rectangle has an area that it's the same as the area under the curve between 2 and 5. And now in this example here, we're asked to find the average value of f on the interval from 0 to 4. So here, the average value function, or f_av, is going to be 1 over 4 minus 0, the integral from 0 to 4 of f of x dx. So here I'm going to get 1 over 4, and now I need to evaluate this integral here, and I have a bunch of geometric shapes. So in order to find the integral, I'm going to go back to the concept of area and to think about all of these geometric shapes here and add them all together. So here I'm going to have 1/4 times the area, so base 1, height 2, so 1/2 base times height, plus base 1, height 2, so 1 times 2, plus, notice these two are symmetric, so if I find 1 I can double it. So I'm going to have 2 times, this is the area of a trapezoid, so the area of a trapezoid is 1/2 the height, which is 1, base 1, so base 1 is 2, base 2 is 1, so 2 plus 1. So I end up with 1/4 times, here I'm going to get 1 plus 2 plus, and here I'm going to have 2 plus 1 is 3, and then 3 plus a half, or sorry, 3 times a half is 3/2, times 2 is 3. So 3 plus 2 plus 1 now is going to give me 6. So 6 times 1 over 4. It's 3 over 2, or 1.5. So finding the average value, so we weren't asked to do anything with the mean value theorem for integrals, we were just asked to find the average value. So it's important to know the difference and to know the formula for finding the average value of a function over an interval.
All right, so we just learned the concept of the average value of a function. And once we learn this concept, a lot of students get it mixed up with the average rate of change notion we learned a while back. So just to put them side by side, the average value of f of x on a to b is the formula we just learned, 1 over b minus a, the integral from a to b, of f of x dx. And some time ago, we learned the average rate of change. This is when we were starting derivatives and talking about the difference between average and instantaneous rate of change of a function on a to b is given by f of b minus f of a over b minus a. Now, if asked to find, and if using these words exactly, find the average value, find the average rate of change, students typically do just fine and know which one to use if these words exactly are given as part of the problem, but typically they're not, and you really have to understand the concept of units. So we're going to look at an example. Let v of t equal t squared minus 2 feet per second. So I'm given a velocity. Use both the average value and average rate of change formulas to find the average velocity on 0 to 2. Hint, use units. All right, so we're being asked to find the average velocity. Now, this formula here tells us the average value of a function. I'm being asked to find the average of velocity. The name of the velocity function is v of t. So average value of f of x is just like asking us to find the average value of v of t. So using the average value formula, so the average value of v of t is 1 over, so the interval is 0 to 2, so 1 over 2 minus 0, the integral from 0 to 2 of v of t dt. So I was asked to find average velocity. The velocity is v of t. So it's like find the average of the velocity function v of t on 0 to 2. It looks just like this setup. Now, we want to double check our units and make sure that this is going to work out. If I want an average velocity, my answer better be in feet per second because I want an average velocity. So let's make sure that our units are going to work out correctly. So v of t, so let's draw a function. V of t, well, time is in seconds, and v of t is in feet per second. So if I find the integral from 0 to 2 of v of t, so here's my v of t function, the integral is going to give us an area where the units of the base and the height cancel. So the base is in seconds, the height is in feet per second. So this integral here is going to give us units that are in feet. And we want feet per second. We want an average velocity, but now we have to remember that this 2 minus 0, this portion here, is in seconds, and it's in the denominator. So in other words, this portion here is feet, and then I have 1 over seconds. So my answer is going to be a number in feet per second, which is what I want because I want an average velocity. So that was using the average value formula. Now let's use the average rate of change formula. So if I want the average rate of change of f of x on a to b, that's given by f of b minus f of a over b minus a. So the average rate of change of the position function is what's going to give me velocity. So here's what a lot of students want to do. So right now I'm trying to use the average rate of change formula. So here's what I'm going to get a lot of. Oh, I need average velocity. Let's do v of 2 minus v of 0 over 2 minus 0. This is incorrect. And again, let's think about units here. So v of 2 minus v of 0 is two velocities. So this is like feet per second minus feet per second over 2 minus 0 is in seconds. So the top is feet per second and the bottom is in seconds. So this is going to be feet per second times, this is like seconds over 1. So 1 over seconds, I'm going to get feet per second squared. This is an acceleration. So this is not the average rate of change formula I'm setting up. So remember, the average velocity is the average rate of change of the position function. So what I need to do instead, so this was entirely wrong. If you wrote it down, erase it so that it's not in your notes and you don't ever get confused with that again. The average rate of change formula, if I were to use that to find average velocity, that's going to be s of 2 minus s of 0 over 2 minus 0. So s of 2 is the position. So the position has to be in feet, right? Where is something at? It's a unit of location, so feet is going to need to be used. So this is feet minus feet. Whoops, shouldn't have put it in parentheses. So feet minus feet over seconds. So s of 2 is a location in feet minus s of 0 is a location in feet. So feet minus feet, so some number of feet minus some number of feet is still in feet over seconds, feet per second. This is a velocity. So my two possibilities for setups are this one, so 1 over 2 minus 0, the integral from 0 to 2 of v of t. If I use the average rate of change formula, now I need s of 2 minus s of 0 over 2 minus 0. So this is average velocity. And if you go back to the chapter where we first learned about this, you'll see this formula. Average velocity is the change in position over the change in time. And then you'll also see average acceleration is the change in velocity, so v of b minus v of a over b minus a. So the change in velocity over the change in time. And we just went through that process and found, of course, that in this example we get feet per second squared, which is a unit of acceleration. So now that we're just, building on all of these concepts and topics, if you see the word average, you need to understand which one you're applying. Now, in this case, there were two different methods to find the average velocity. I could use either of these formulas, and some problems lend themselves to using the first formula, and some problems lend themselves to using the second formula. So it, of course, depends on what you've been given. So let me just go ahead and pose the question now. In this particular problem, which would be the easier one to solve, or which one can I use to solve this problem of find the average velocity? Well, notice what I'm given. I'm given the velocity function, so it would be impractical to use this second formula. Although this formula would work, it requires the position function. And we don't have the position function, we have the velocity function. Can we find the position function explicitly? I hope your answer is no, because we don't have an initial condition. So v of t is t squared minus 2. I can integrate to get position, but I'll get a plus c, and nowhere in this problem gives me a way to get rid of that plus c using an initial condition. So I'm stuck using the average value formula to find the average velocity on this interval from 0 to 2. So hopefully that concept is a little straightened out now. If you need to review the concept of average velocity, I would challenge you to go back, and this was covered back in chapter 3 in section 3.4 in first semester.
And now let's take a look at an AP multiple choice question. So the average value of cosine x on the interval from -3 to 5 is which of the following? So this is a really straightforward question, knowing the formula for the average value of a function over an interval. So 1 over b minus a, so 5 minus -3, the integral from -3 to 5 of cosine x dx. So now 1 over 5 minus -3, that's going to give me 1 over 8. And then I'm evaluating the integral from -3 to 5 of cosine x dx. So now the antiderivative of cosine, so let's bring down the 1 over 8, is sine x evaluated from -3 to 5. So I have 1 over 8, And then here we're going to substitute in 5. So sine 5 minus sine of negative 3. So now what I have is sine 5 minus sine of negative 3 all over 8. Now, is that an option? So if I look up here, I have the two options with 8 are A and D, and neither of those are it. So did we do something wrong? So the answer is no, we didn't do something wrong. It's just that there's a bit of simplifying that we're going to need to do here. And it goes back to a pre-cal topic of knowing that the sine function is an odd function. And knowing that if I have sine of negative x, that's the same as negative sine x. So here, if I have sine negative 3, it's the same as plus sine of positive 3. So the answer here is actually E, and it's knowing this property of the sine function. So sine of negative x is the same as negative sine x, and cosine of negative x is just cosine x. So the negative just goes away entirely. So these are two properties back from pre-cal that I wanted to touch on for a second, just to go back and remember them because they do come up on the AP exam.